Welcome to the Walton Pi. What you're about to see is a review I taught for multivariable calculus at Brigham Young University. We covered multiple integrals and how to calculate them, the Jacobian, and how to do some change of variables. Hope it's helpful and enjoy.
Let's go over surface area, if that's all right.
Yeah, let's go ahead and do that. Okay, so here we go. So for surface area, the general rule for this is that you can always find the surface area by doing the double integral over some domain of the square root of your derivative of f with respect to x squared plus the derivative of f with respect to y squared plus 1, then times your dA. So this is your general form for surface area. So for example, let's say that our function is f of x and y is equal to 3x squared plus 2xy plus y squared. And we are trying to figure this over the square where x goes from 0 to 3 and y goes from 0 to 2. So just a little box, and we're trying to find the surface area of this function over that region. What we can do is we can find the surface area by plugging this all into our equation for the integral. So we would get the integral over our domain. So maybe we go x first, so 0 to 3, and then y 0 to 2. So we know we're going to be dx dy at the end. And then we just look at what is the square root of the derivative of f with respect to x squared plus the derivative of f with respect to y squared plus 1. So if we go through and figure out what those different things are, the derivative of f with respect to x is going to be a 6x plus 2y plus 0, so that's our f sub x. Our f sub y is going to be, let's see, we get a 2x plus 2y squared. Or not 2x plus 2y squared, just 2x plus 2y. Squared, and then we add a 1. And all of that under the square root, this is going to give us the surface area. This doesn't look like it's going to be a super pleasant thing to try and integrate, but however we would be able to go about doing it, that would give us the surface area for this region, so some sort of like weird thing over the rectangle 0 to 3 and then 0 to 2, where all of these are just falling directly over the edges. So figuring out what this surface area of this region is.
Sweet, thanks.
Okay, did that answer your question about surface area?
Yeah, that was helpful.
Okay. Any other topics you wanted to go over?
Changing the order of integration?
Yeah. So changing the order of integration. What we can then do is if we are trying to change our order of integration, this usually depends on what region we are looking at. So let's say that we are, so in 3 dimensions, so we have, this is the plus x direction, the plus y direction, and then the plus z direction. So we have this region, and let's say that we are trying to integrate over this solid region here. So where this is, all of these points are at 2. So that's sort of like triangular prism shape. Or not triangular prism, just this like triangular pyramid sort of shape. We're trying to figure out how we can integrate that. And so our bounds are going to depend on which ones come first and second and third. So let's say that we were going dx, then dy, then dz. So we need to figure out what are our x values going to go between, what do our y values go between, and then what do our z values go between. Some problems it's easiest to work from x's to z's, other times it's easiest to go from the z's to the x's, so like outside in or inside out, depending on the problem. This one is probably going to be easiest to go outside to the in, so here we would start with what does z range between. So here we can see that z starts, the smallest z can ever be is at 0, and then the biggest it can ever be is out here at 2. So we can say that z is going to range from 0 to 2. The next thing is we might want to figure out what does y go between. Well, we might be tempted to say, well, it just goes from 0 to 2 again. But if we were to do that, that would give us this box shape in our z-y axis plane. We would get a box, but we don't want that entire box. We just want this part of the triangle section. So we know we can't go from 0 to 2, but we have to instead figure out what line is this line that is our top of our y function. Because the bottom of y is always at 0, but the top of y is going to go up to something. So if we figure out that this is at +2 and this is at +2, we can figure out that the top is going to be the value or the line 2 minus z, because that is this line up here. That line is y equals 2 minus z. And so that gives us what our y value is going to range between. The next challenge is then when we add in x, we could be here and it would go up to some random point here in the middle of that triangular slice. So we have to figure out what plane is our upper bound for x. So we are trying to figure out what plane is this that's right there. What we can do is we can figure out this based on our 3 vertices. We know that when x is, or when y and z are 0, x is 2. When z is our only one that is not 0, it's also 2, and then when y is our only one that's not 0, we get 2 as well. So we find that our plane is going to be x plus y plus z is equal to 2, which makes it so that we can solve that the plane is going to be x equals 2 minus z minus y. So that is going to be what our upper bound is going to be for x, 2 minus z minus y, and our bottom bound is going to be 0. So for this region, that's how we can figure out what our bounds of integration are going to be. If we were to want to switch the order of integration, what we would first have to do is figure out what region we're looking at, then switch the variables into the order that we want, and then figure out what bounds are going to be on our new values for x and y. Because if we were to switch x and y in this, so where y comes before x, so we get dy, then dx, then dz. If we were to do that, now we can't have the exact same bounds that we had. Our z bounds are still going to be the same, but our x and y bounds will change. It turns out that they don't change a huge amount because this problem is very symmetrical, but x is going to go from 0 to 2 minus z, but then y goes from 0 to 2 minus x minus z. So very similar, but they do change a little bit. Did that answer your question with like how to change bounds of integration?
Yeah, that was great. Thanks.
Awesome.
All right, can we do a problem from 15.8, a triple integral in spherical coordinates?
Yeah, triple integral in spherical coordinates. Let's see, do you care which one, do you have one in particular you want to do, or do you just want to do one?
Maybe 23?
Can we do number 23?
Yeah, is that this one where it's the triple integral over a ball of, let's see, x squared plus y squared plus z squared squared dv?
Yep, and that's the one.
D is centered at 0 and has radius 5?
Yeah.
Okay, perfect. Yeah, so if we want to integrate this over spherical coordinates, we first need to make our substitutions. So we can make our substitutions for x, y, and z. So x is going to be rho sine phi sine theta, I think. Let me just pull that up and double check. Oh, this is rho sine phi cosine theta. Sorry, got that one backwards. Y is rho sine phi sine theta. And then z is rho cosine phi. This dv is thought of as like a dx, dy, dz. And do you remember the substitution that we make when we are trying to figure out what that would be in spherical coordinates?
Do r dr d theta.
Well, that'd be,
So that's
for polar. What if,
Oh,
for spherical coordinates, it's
Oh.
just a little bit more complicated.
that's true, that's true.
that's the rho squared sine phi.
Yeah. So that is going to get replaced with a rho squared sine phi. Come on, right. Yeah, so that's going to get replaced with a rho squared sine phi, then the like d rho, d theta, d phi, whichever order we put them. So that's what that piece is going to get substituted for. Do you know what x squared plus y squared plus z squared is in spherical coordinates?
I'm guessing it's a sphere.
So, yeah, those are going to be the spheres, but specifically it gives us the radius squared. So if you didn't know that off the top of your head, you could square x, you could square y, and you could square z and add them together, and you would be able to combine them in such a way that you would see that this piece turns into an r squared. So we get r squared, or not r, that's polar, rho squared, and then we square it again, so we are going to have a rho to the 5th from that piece. And so what we then have,
Why is it rho to the 5th rather than rho to the 4th? Are you already integrating it?
Yeah, you are right. That is a very bad verbal typo. You are right. 4th. Thank you very much. So we get rho to the 4th times rho squared sine phi d rho d theta d phi. Now we just have to figure out what are our bounds of integration on these different integrals. So we have rho is the incident one, then we had theta, then we had phi. So in this case, we are having a ball centered at 0 of radius 5. So that tells us we want rho to go from 0 to 5.
Yeah.
We then want to have theta, because theta is, let's see, so if we were to draw the sphere, where this is like our z-axis, we have our sphere. Theta is measuring this distance going around the axis, so we want the full 2 pi to be able to get all of it. So we are going to have theta go from 0 to 2 pi, and then phi measures the angle down from the z-axis, and we want all of that one as well, but phi only goes from 0 to pi, because if we were to go past pi, we would then be double counting some of the stuff at the bottom of the sphere.
It makes sense.
And so that gives us the setup for our integral. we just then need to figure out what is that going to be equal to. So clearing up a bit more space, we get that this is going to be equal to the integral. Let's see, we got 0 to pi, 0 to 2 pi of, 0 to 5 of rho to the 6 sine phi d rho d theta d phi. Well, if we just look at our insidemost integral, we are integrating rho to the 6th times sine of phi with respect to rho. It tells us that we can kind of treat the sine of phi as a constant because it doesn't have any rho's involved. So when we integrate that, that is going to turn into, so just that one piece, that's going to be a rho to the 7th over 7 times sine of phi, but then we evaluate all of that from 0 to 5. So we are going to get 5 to the 7th over 7, 5 to the 7th over 7 times sine of phi. And so once we plug that in, we can simplify a little bit by pulling out the 5 to the 7th over 7 to the very front. So we get a 5 to the 7th over 7, and then this inside piece, this integral has been taken care of, so it's now gone. And then this rho to the 7th has also disappeared. So this is what we are left with. We pulled the 5 to the 7th over 7 out to the front, the sine of phi stuck around, and so this is what we then have to evaluate. So, by then looking at the next insidemost integral, we have the integral from 0 to 2 pi of sine of phi with respect to theta. Sine of phi has no thetas in it, so this is just integrating a constant with respect to theta, and by just looking at that is kind of like thinking of we're integrating a 1 with this constant that could get pulled outside to the front of that integral. So we're just integrating 1 from 0 to 2 pi, which is going to pull out another 2 pi term. So we can pull that term out to the front as well. So we now have a 2 pi as well multiplied out front.
Wait, is your mic on? Yeah. Okay, yeah. So I do have a question about spherical as well as polar. Is the annotations turned on? Let me. Okay, so in these situations, could I just do the integral of like, I guess, let me, I can't erase. Let me grab the eraser. Okay, so the integral of dp integral of like d theta, not times but plus.
Yeah, so multiplying them together.
Or it just like, yeah, multiplying them together, not adding them. You know what I said.
So in this situation, because none of the functions have multiple pieces together, we're just multiplying like the rho to the 6th times the sine of phi times something in terms of theta. We could have integrated each of these pieces separately and multiplied them together. That is something that we could have done.
Okay.
In general, though, that might not be the case. Like we might have had like rho plus theta squared, which means that we had some terms that we would have had to deal with to break it out, and so we wouldn't be able to always do that. But in this case, because it was one of those very easily broken apart pieces, we could have integrated each chunk separately.
Okay, I'm happy.
All right. So then what we're left with is now we just have, as we've pulled out the piece from the theta term, we are now left with just the integral from 0 to pi of sine of phi with respect to phi. So the integral of sine is going to be negative cosine. So this all turns into that times a negative cosine of phi evaluated from 0 to pi. Cosine of pi is -1, so that's going to be, so we get, let's see, 2 pi times 5 to the 7th over 7 times a negative of -1, because that's what cosine of pi is, minus the negative of cosine of 0, which is, cosine of 0 is going to be a,
Be 1, right?
yeah. So we are going to get negative of -1 plus 1, so that's a 2, times the 2 pi. So all in all, that's going to be equal to 4 pi times 5 to the 7th over 7.
Boom.
Okay. Any questions with the process for this one?
I'm feeling pretty good.
Yeah, I feel like it made sense.
Maybe do 15.9, question 31 next. The one that we didn't get.
Number 31?
Yeah, because we didn't get to that one.
Alright. Yeah, so let's see. So that one is, so f is continuous on 0, 1.
Yeah, and let R be the triangular region of vertices 0, 0, 1, 0, and 0, 1. Show that the double integral of f of x plus y dA equals the single integral from 0 to 1 of u f of u du.
Mm-hmm. Okay. Yeah, so let's see. So we got the double integral over the region. So that's this region here of f of x plus y dA. And we want to figure out what that is going to be equal to. Okay. Yeah, we can do this. So, because of our region, we first have to figure out what is it going to range between. So if we want to replace the dA with dx dy, that tells us we want our y value to be between two constants. So y is going to range from 0 to 1, and then our x is going to range from 0 to 1 minus y. Because this line here is y equals 1 minus x, or x equals 1 minus y. Those are the expressions for that line. And so that gives us what we are going to be integrating this with respect to. So, if we want to integrate f of x plus y with respect to x, we have to figure out how are we supposed to do that. So I'm pretty sure we are going to need to do, let's see. I think we are going to want to be doing a special substitution and then use a Jacobian to figure out what dx dy turns into. Our goal is to get it to be an f of u sort of situation. So we want to, that tells us what substitution we want to make into our problem. We want to say u is equal to x plus y. So we can then be able to make that substitution. The next challenge, though, is we have to then figure out what we want our other substitution v to be equal to. Because we do have to make a second substitution. The problem is going to be, what do we want to make our substitution be? I think if we just make the substitution be x minus y. No, that would make the region hard. Alright. What I'm trying to figure out now is to figure out what we want our second v to be. It has to be something that is not a scalar multiple of u, so it's something that's going to be pointing in some other direction in R2. But ideally it's something that would be easy to help us with our integral. So right now we have this line is going to be represented by like x plus y equals some value. So like x plus y equals 1 is going to be the very outside region. What we will want to see, so I think maybe if we just make v equal x minus y, would that help? Yeah, I think if we make vx minus y, this will work out. The way that we then figure out our, so this turns into an f of u, but then we have to figure out what our bounds of integration are. Let's see, we'll figure that out in a sec. Let's see, so do you remember the way that you find the Jacobian?
I know that you take the derivative of x with respect to u and v, and the derivative of y with respect to u and v, and then you
Take the determinant.
yeah, the determinant. I knew what the operation was, just didn't remember the name.
Yeah, so yeah, you're absolutely right. So that tells us we need to figure out what is x in terms of u and v, and what is y in terms of u and v.
Yes.
If we want to get just x using these two equations, if we add the two together, so we get a u plus v, that is equal to 2x plus 0y.
That makes sense.
So then we can say that that means that x is u plus v over 2. If we want to get y, if we take the first one and subtract the second one, then we would get u minus v equals 2y. So we find that y is u minus v over 2. And so yeah, now that we have what u, or what x and y are in terms of u and v, we can put those into a matrix to figure out the Jacobian. So that is where you take u with respect to x, draw. Okay, so u with respect to x, u with respect to y, v with respect to x, and then v with respect to y. If we take the determinant of that, that's going to give us what we will replace dx dy with. So if we look to see what is u sub x, that's the, x sub u's, pardon me, I wrote this all wrong. This is x sub u, x sub v, y sub u, and y sub v. Sorry.
I do have a question now, okay? So, I guess it doesn't matter. Or maybe it does. So, in the textbook, it shows that matrix kind of flipped around the diagonal axis.
Like things switched like that direction?
Yeah.
Yes. That gives you the same result. It doesn't matter which order you have them.
Okay, I didn't think it did because...
all the x's in a row, then all the y's in a row, or all the x's in a column, then all the y's in a column. It gives you the same result.
Okay. Yeah, that makes sense then.
Yeah. So now that we have it in the correct form, as opposed to the incorrect form earlier, we can figure out what those things are going to be. So the derivative of x with respect to u, that is a 1/2. X with respect to v is a positive 1/2 again. X with respect to, or y with respect to u is another 1/2. And then y with respect to v is a negative 1/2. And so when we take the determinant of that matrix, we find that this is equal to, let's see, 1/2 times negative 1/2 is a negative 1/4, minus 1/2 times 1/2, so minus 1/4, so is equal to a negative 1/2. And so what we get is we are going to have this integral turns into whatever our domain is now in terms of x and y, then of f of u times a negative 1/2 du dv.
Now, with Jacobian, don't we take the absolute value of that, so just be a positive 1/2?
No, the Jacobian can be negative. Yeah, the Jacobian can be negative. These bars are just signifying taking the determinant of this matrix. So there's not absolute values involved. So yeah, the Jacobian can be negative, and in this case it is.
Okay.
So now that we've gotten that, we just have to figure out what are our bounds now in terms of our u and our v. Because what we used to have is we had y goes from 0 to 1, and then x goes from 0 to 1 minus y. We can't keep those bounds because those are going to no longer be correct. So now we have to figure out what are our bounds in terms of our new variables u and v. So we already know that if u equals 0, we are looking at sort of this line, and then we are going to be incrementing our way up into these lines farther and farther out. So one way that we could think of this is if we kind of keep the same region. Here, let's just redraw it. So if we keep the same region, so we are still looking at this region here, but now instead of our axes being x and y, our axes are going to be u and v. So if we draw our u-axis, when u equals 0, this is the line u equals 0, and then we get out to this edge of the triangle, and this is u equals 1. So this is one of our axes. That blue line is going to be actually our v-axis. The next thing we need to figure out is what is going to be our other axis. So we figure out when is v equal to 0. And that's going to be when y equals 0. So this is going to be our second axis. So this direction is plus u, this direction is minus u. Then we have to figure out, well, which direction is the plus v direction. So if v is 1, for example, so we say 1 equals x minus y, then we find that that is the same thing as the line y equals x minus 1. So that is going to be this line down here. So this is going to be our plus v direction, and this is our minus v direction.
Makes sense.
Now that we have our axes, we can figure out how can we draw that triangle in terms of our axes. So we might be able to figure out that these points, so let's draw a couple of these points here. So right here is this is at 1, this is at negative 1, and this point up here is also at 1. So this line right here is the line u equals, I don't want to draw there. That line right here is the line u, well, I want to draw anywhere. That is the line u equals negative v. You see how that's going to be, oh, yeah. That's the line u equals negative v.
Yeah.
And then this line over here, this is the line u equals v. So if we were to integrate this, so we have our -1/2 integral of f of u d, let's see, the u is the nicest one to go between, so we are going to have u be the second thing we integrate, and dv comes first. The reason u is nice is because it goes from 0 to 1, rather than these weird triangle shapes. And so that tells us that we can say, well, v is going to go from, so let's solve this one, so this is v equals -u. V is going to go from -u to +u, and then u is going to go from 0 to 1. Does that make sense?
Let me look at it a little bit more. Okay, yeah, no, that makes sense to me.
Okay. So now that we have that, now we just have to integrate that and figure out what that's going to turn into. So, if we integrate the insidemost one, we are integrating something in terms of only u with respect to v. So we can essentially just pull that u thing out and just treat it as a constant. So we are integrating 1 from -u to u with respect to v. So that's going to turn into, we have a -1/2 out front, integral from 0 to 1 of, the integral of 1 with respect to v is just going to be v, and then we evaluate v, so it's v evaluated from -u to u, du, oh, forgot the f of u is acting as a constant, so we have f of u du. Now v evaluated from u to -u is going to just be 2u. So we get a 2u right there. So these 2's can cancel. So that 2 cancels with this 2, and so we just have that -1 out front. And so we're off by a sign from what the book asked us to show. So where is our sign error? Okay, my guess is that this up here is not actually 1, but is -1. So let's see if we can figure out if that's actually where our error is. So let's see if we can figure out if that's our mistake. So let's see. So that line is the line y equals 1 minus x. So we get x plus y equals 1, but that was our u substitution. We did say u is x plus y, so that is u equals 1. How are we off by a sign?
So I was thinking that Dr. Swenson said that you always have to take the absolute value of the Jacobian. That's why I said that. I thought he was saying if it's negative, you have to.
Okay, so let's see. So I don't think you take the absolute value of the Jacobian, because in the book, example 3 in 15.9, the Jacobian's a negative. by some sign somehow. Oh, you are right. When you put it into the integral, you take the absolute value, but finding the Jacobian itself, there isn't an absolute value. So the
Okay.
Jacobian without the absolute value, when you put it into the integral, you do take the absolute value. So that means that we should not have had this negative sign out front to start with.
Got it.
I've got a question that's kind of maybe a little pointless.
Uh-huh.
When we find the Jacobian, that's the Jacobian, and then when we plug it into the integral, Professor always refers to it as the fudge factor. Is that like a real name, or is that just him?
So I've heard other people call it that. It's a common nickname for it. So calling the Jacobian the fudge factor is like, I know it's going to be changing my variables to like du, dv, or d theta, dr, or d rho, d theta, d phi. And then you just have to figure out, like, it is that, but then it's being multiplied by something else. And so you figure out, what do I have to multiply it by? So calling it a fudge factor is one way to remember there's something other than just changing the variables I have to stick in there.
Okay.
Yeah, it's mainly just like what people like to call it or refer to it as. Thank you for watching. Hopefully this video was helpful. Please check out some of my other videos and like and subscribe, because that helps me out quite a bit to be able to continue to make these videos to explain different concepts of mathematics. Hope you have a wonderful rest of your day, and good luck with all of your other math.